Hello, back again to Engineering 201, Electrical Fundamentals, and picking up where we left off last time, working on transient problems using that six-step method. We tackled a fairly easy problem last time. I want to work on a more difficult problem. Maybe that's not a good description. Maybe I should say a longer problem, a little more tedious. We'll then, after this one, not in this lecture, but the following lecture, do one final problem in this that will include a dependent source. So we'll get some practice with that. But this problem here, you see that we have a current source, a voltage source. We've got a switch here that's initially closed, and we've got an inductor. So last time we worked a problem with a capacitor. This time we're working a problem with an inductor. So what we'd like to find is the voltage across this 2 ohm resistor out here as a function of time. So that's what our task is. One thing's kind of interesting, this switch that is shorted out, it's actually shorting out this source here. That's probably not a very good thing to do in real life, trying to short out a source. Although I wouldn't necessarily say this is a bad problem. You would certainly want to do this on a source or a battery or something, but if we were wanting to try and model what would happen if you did do that, maybe this is a good model in that sense. So from a practical sense, you don't want to take a wire and put it across the terminals of a source, but for an analysis we might come up with some interesting results. Well, let's go ahead and get started with it then. Step number one would be to say that the solution is of the form that the voltage here, I guess we could we might start out with what x of t is equal to k1 plus k2 e to the minus t over the time constant, and we could then customize this, so to speak, for our problem. We're looking at the voltage, so the voltage as a function of time would be equal to that k1 plus k2 e to the minus t over the time constant. So again, our task is going to be to find the time constant, K2 and K1. Well, is this an okay model? Well, we have a DC source. We only have one energy storage element, that 2 Henry inductor. 2 Henry inductor is a fairly large inductor, but it's not uncommon. We've got some 1 and 2, and I believe 5 or 10 Henry ones down in lab, so it's not completely unheard of. I think we're okay with that. One energy storage element, DC source here, DC source there. We're good to go. We've got 2 sources. That's not a problem. If we had 2 inductors and we couldn't combine them into one, that would be a problem. So with this thing shorted out, this point here effectively becomes that point there, which really collapses much of the right-hand side of that circuit, doesn't it? So we end up, if we were to look at part number 2, assuming the switch has been closed for a long time, and we want to find the current through this inductor, what's that going to look like? Well, let's see. If I short this thing out, then this point, which we said this point here, if we take this as our ground, is with this shorted out, it's essentially the same as that, isn't it? Which if we short this out, because we're going to look at the inductor as a short, so looking at that inductor as a short, we short that out, then this point becomes the same as that point, which is the same as that point. So I have ground there, don't I? So let's see what this starts to look like. I've got that 12-volt source. I've got 2 ohms of resistance there, and then I'm going to have this 2 ohms of resistance here, and then effectively I have this short that goes right to ground. Okay, and I could talk about this then being the current through the inductor. I better keep that lowercase. So I'm going to call this I of L. Okay, and this is 2 ohms and 2 ohms. Now we see any current getting to this point is not going to go through that 2 ohm resistor. It's going to go through this dead short. So we have effectively removed that, but I left that in just so we can see it a little better. So I could say that this is really equal to what, 12 volts divided by 2 ohms, which gives me 6 amps. Okay, and this is for time. Time equal to 0 minus before we move the switch. Okay. Well, let me use some real estate here to build our scorecard. So we're going to say that the inductor is equal to 2 henries. And we just found that I through the inductor at t equals 0 minus, if you will, is equal to 6 amps. Well, with that, we're ready to move on to number 3. Step number 3. So if we look then at step 3, we'll call this step 3. Step 3 says to replace this current source, and I found this current source actually going this way, right? And if I look at that, I had that thing going like that, so it's going to the right. So I'm going to replace the inductor with this current source, and I need to be careful which direction it's going. I found this current going to the right, so I need to replace it with a current source that's going to the right. And what value is that? That's at 6 amps, isn't it? So I've got 6 amps there. I've replaced that. I've opened the switch. So in step number 3, we throw the switch, we move it to the new position. In this case, it's open, which is current source we'll like a lot better. And now we can start to analyze this. And this is where it's going to probably maybe get a little bit tedious. I'm going to have to probably use a node or mesh. I think probably node analysis is a good plan for this one. So I'm going to take this as a reference ground. I'm going to say that this is point number 1. I'm going to say this over here is point number 2. And I could talk about, if you will, I1 there. And maybe we'll talk about I naught. I guess I didn't say I. So I naught, I1. Why don't I put I2 here? We've got 6 amps there. We've got 4 amps. So I can call this I3. Maybe I'll put it like this. A little bit backwards, but that's okay. That'll be kind of interesting for us. Normally I usually put that down, but we'll call that I3. So I could say Kirchhoff's current law at 1 gives me the equation. I got I1 leaving, I naught leaving, I2 leaving, and 6 leaving. So I naught plus I1 plus I2, not I1, I2 plus 6 is equal to 0, right? Okay, and I can start to make my substitutions. What's I naught going to be? That's going to be equal to V1 divided by 2. Plus I1, now I need to find that voltage there. It's going to be a minus 12 plus V1. V1 minus 12 divided by 2. Plus I2, I have to find that voltage, which is going to be minus V2 plus V1 over 2. So unfortunately I got a V2 in there. One equation, 2 unknowns. You know what's going to happen now. And then I'll say plus 6 is equal to 0. So I think I'm okay with that. V1 minus 12, V1 minus 2, yep. So let's see. I could multiply everything by 2. So I have V1 plus V1 minus 12 plus V1 minus V2 plus 12 is equal to 0. How many V1s do I have? 1, 2, 3. 3 V1 minus V2 is equal to, let's see, I had a plus 12 and a minus 12, so that's equal to 0, isn't it? So nice little equation, but still 2 unknowns. 3V1 minus V2 is equal to 0. Now I'm going to have to do Kirchhoff's law at 2, right? So Kirchhoff's current law at 2. What am I going to get with that? I got 6 going in, and I got 4 leaving, and I got I2 going in, and I got I3 going in. So I'll say 6 plus I2, because that 6 is going to come up there. The I2 is going in, plus I3 is equal to 4. Is that right? I3 is going in, 6 is going in, I2 is going in. Yep. So I've got 6 plus I2, which I found I2 to be this thing right here, V1 minus V2 over 2 plus I3. Now I have to be careful with this one. I3 is going that way. So I need to find the voltage opposite that, which is going to be minus V2, isn't it? Minus V2 divided by, if I combine these resistors, I will have 4. Now we could talk about V0 here, but I'm not going to introduce that as an unknown. I'm just going to find V2 and then divide it, use voltage division to get V0, because that's what I'm really looking for. So I've got that is equal to 4, multiply everything by 4, I have 24 plus 2 V1 minus 2 V2 minus V2 is equal to 16. So I have 2 V1 minus 3 V2 is equal to minus, let's see, is that right? Minus 8, right? Okay, so what I'd really like to find is V2, right? So I think I'll multiply this equation by 3. So I've got 6 V1 minus 9 V2 is equal to minus 24. Now I think I'll multiply this equation by 2, or shall I say minus 2. So I'll multiply it by minus 2. When I do that, I get minus 6 V1 plus 2 V2 is equal to 0. Did I do that multiplication right? 2 times 3 is 6, minus 3 times 3 is minus 9, minus 8 times 3 is minus 24, minus 2 times 3 is minus 6. Excuse me, minus 2 times 3 is minus 6, yeah. Minus 1 minus is plus 2. So when I add these things up, I get the V1's canceling out, that's good, and I have minus 7 V2 is equal to minus 24. So coming up here, V2 is equal to 24 over 7 volts. So therefore, V0 is going to be equal to V2, because by voltage division, just be an even split, wouldn't it? I mean, that's 2 divided by 4. That's what our half looks like, doesn't it? So V0 is equal to 24 over 7 divided by 2. So when I go through that, I think I'll get a decimal here. Just work it out that way. Okay. There we go. So I get 1.71 volts. Okay, 1.71 volts, and that's so I say finally that V0 at t equals 0 or 0 plus, just after the switch is thrown, is 1.71 volts. So I can put that back in the scorecard. V0 t is equal to 0 or 0 plus is equal to 1.71 volts. Okay, so that's what I was looking for. And like I said, these problems come up at a great point in the term as we're starting to think about getting ready for the final and things like that. Good practice here. If you can do a problem like that, you're starting to really have some proficiency in node analysis. Well, let's go on to step number 4 then. Step number 4, what we do as we go from step number 3 to step number 4 is we just wait. We've got to let some time go by, because remember that at 3, t was equal to 0 or 0 plus, and at 4, t is equal to infinity. Okay, or what's that? T equal to 5 time constants. So how do I do that? Well, as we wait, as we go to steady state, the inductor Starts to look like a short, doesn't it? So we've got that inductor shorted out. You'll note the switch is still open. Once we open the switch, we never change the position. So I have something like that. Well, again, what do I have going on here? If this point is a dead short to that point, this resistor is effectively removed. So I can remove this. I've taken the switch out because it was open, just to kind of clean it up. The rest of it stays about the same. So what I need to do now is I need to find this. Well, back here on this one, we were looking for V at t equals 0. Here, we're looking for what? V at t equals infinity. Okay, so we've got V at t equals infinity. So how can I do that? Well, more node analysis. Take this as the reference. We'll just put this up here. We'll say that that is V. And again, if I can solve for that voltage V, I think if I divide that between these resistors, we're good. This, in other words, that's that voltage across there. Well, I can put some currents in here. Let me call this I1. I1. Let me call this, I think what we have that as I0 before. This is going to be 4, and we could call this, we'll mix this up, we'll call this the other direction, I2. So I can say, with Kirchhoff's law, and I really only have one essential node, this is all one node up here, isn't it? So I've got I1 plus I0 plus 4 plus I2 is equal to 0. Is that right? This is all one node, one great big node. I1's leaving, I0's leaving, 4 is leaving, and I2 is leaving. So obviously couldn't have everything leaving, so probably one or more of those is negative. Okay, so I1. Do we have I1? We need to find the voltage going that way, don't we? So we have V minus 12 over 2 plus I0 is going to be V over 2 plus 4 plus I2. Now this time I have to go this way, right? In the last problem I went the other way because I took I3 going the other way. Just mix it up. Here I've got I2 going this way, so I've got to find the voltage opposite it. The current's going that way. The voltage potential has to be opposite, so that's going to be V divided by, this time again I have to add those up. It's 4 is equal to 0. I multiply the whole thing by 4. I have 2V minus 24 plus 2V plus 16 plus V is equal to 0. So how many V's do we have? We have 2 of them, 4 of them, 5V is equal to, the 24 goes over as positive, the 16 goes as negative, so I have 8. So I could say then, moving this up to here, that we have V is equal to 8 over 5. So V naught at t equals infinity is going to be equal to V. I just have to divide this, right? Times what? Well, it's voltage division. It would be this resistor 2 divided by the sum of the 2, which is 4. That's, of course, that's our half. That's where we get that even split, that 1/2. So I can say that V naught at t equals infinity is equal to 8 over 5 divided by 2, which gives me what? 0.8 volts. Okay, 0.8 volts. So I'm going to go back and I'm going to put that in our scorecard here. V naught at t equals infinity is 0.8 volts. Okay, so I've got that. So we're on to step number 5, right? So step number 5. What's 5 about? 5 is about finding the time constant, finding the equivalent or the Thevenin resistance, which oftentimes we get via the equivalent resistance. Can we do that with it? Yeah, we can use the shortcut. with the shortcut, how do we, well, certainly the reason that we can use the shortcut is we don't have any diamonds, right? So we don't have any of those things, so we can use the shortcut. We should be pretty happy about that, because if we can't, then the last problem we're going to do in this section will be a problem where we can't do that. And it's not all that bad, it's just more work, more analysis, more tedium. But again, at this point in the term, that's not necessarily a bad thing as we get more and more practice doing this analysis and getting really good at this as we look at trying to pass the final. Well, using the shortcut, we're going to want to do what? Short voltage sources. Short voltage sources, open current sources. And then look back into the terminals. This is where the inductor was. We'll look back into those terminals, right? So if I do that, if I short the voltage sources, and what else am I going to have? That's open, so I won't concern myself with writing that. That's a current source, so that's going to get opened. And I still have this one up over the top, don't I? So I've got 2 ohms, that's that one. 2 ohms, that's that one. 2 ohms there, and of course these 2 ohms here. I've shorted out the voltage source and I've opened that current source. That's open there. If we wanted to put that in, we could put that in. That's where that current source used to be. So then I look back into these terminals and I try and come up with the equivalent resistance, don't I? Remove this so I don't get distracted there. Well, what do we have? Well, these two are definitely in parallel, aren't they? So I have 2 in parallel with 2, which gives me 1 ohm. And I would say that these would be in series. So 2 ohms plus 2 ohms gives me 4 ohms. So like I've always mentioned, redrawing is really important when you're going through these. I see when students make mistakes, it's oftentimes that. So let me do just that. I've got that 2 ohms up top. And then I've got this 1 ohm that I just found. And then what do I have here? This is open, so I'm just going to have something like that, where I have 4 ohms. So I got those 4 ohms, that 1 ohm. These are in series, so I can say that I have essentially 1 ohm plus 4 ohms. And that's going to be then in parallel. This series combination is in parallel with 2 ohms. So I have 5 ohms in parallel with 2 ohms. Product over sum, right? So I get product over sum, 10 divided by 7 ohms. I think I'll get a decimal equivalent for that. 1.43, yeah, 1.43 ohms. Okay. So I could come back to the scorecard here. I've got R equivalent, which is equal to R Thevenin, is equal to 1.43 ohms. 1.43 ohms, and that's how we got it. Now, what do I want to do with that? Well, I want to use that to get the time constant. I know that the time constant is equal to, and usually it's what? Thevenin times the capacitance. Well, this is an inductive problem, so it's the inductance divided by the Thevenin or the equivalent resistance. So good thing I got my scorecard here. I've got 2 henries That's the inductor, and the Thevenin 1.43 ohms. And again, I want to use base units. If they've given it in millihenries or something, or you're in k ohms, be very careful of that. I've got base units here, so I should be able to turn this out. As 1.4 seconds. Okay, 1.4 seconds. So time constant is equal to 1.4 seconds. So the last step, 6, is to put this whole thing together. And what page are we on? 5, so page 5 with step 6. The last step is put this whole thing together. So I can come back to my scorecard here, and we're trying to find the voltage. So I know that K1 is going to be equal to what? This 0.8 volts, 0.8 volts. And then K2 is going to be equal to what? K2 is equal to the voltage at time equals 0 minus K1. Is that right? Because when we said that voltage at time equals infinity is equal to K1, and the voltage at time equals 0 is equal to K1 plus K2. So we have this one. That one's done. So then I take this one. We had 1.71, and that's going to be equal to K1 that we had was 0.8. So 0.8 plus K2. So we can say down here that K2 is equal to this 0.8. Did I get that right? No, sorry. That would be the 1.71. So 1.71 minus the 0, the K2, because this is your, oops, how did I mess this up? Double check this. I've got K1 is at infinity. That's this. And then K1 plus K2 is the value at 0. So the value at 0 is 1.71. Good. And K1 is the value at infinity, 0.8. So 1.71 minus 0.8 is equal to K2. Yeah, I was just rearranging this equation here. Good. Okay, so when I go through that, what's that turn out to be? 0.91, 0.91. We've got 0.8. Why don't we just call that 0.9? Call that 0.9. So I can say then that the voltage V0 of t as a function of time is equal to K1, 0.8, plus 0.9, or 0.91 if you prefer, e to the minus t divided by the time constant, 1.4. And you could flip that over if you wanted to. I think I'll leave that like that. This would be volts. And I have then a final answer there. Okay, so let me double check that. 0.8 plus 0.9 e to the minus t over the time constant, 1.4. So again, fairly long problem, but not super difficult. One of the things I would recommend again is to keep the scorecard so you have your values. You're not mixing them up with ones from previous problems and things like that. So we're going to do one last problem in this area where we'll tackle a problem that has a dependent source in it. Not all that difficult, but longer yet. So we'll go through that when we get to when we meet next time on video, and tackle that before we finish up our last section on Introduction to AC Analysis. So again, I can't emphasize enough. Start some of these homework problems. They can be kind of long, but they're also good in terms of reviewing for the final. And I'll talk to you next time. Take care. Till then, thank you for watching.